Assalamu alaikum. Data security and encryption lecture number 5. This lecture is in the continuation of previous lecture about information and number theory. In the last lecture we discussed about the divisibility and division algorithm, and we discussed some properties of division and divisibility. We concluded the lecture with the implementation of Euclidean algorithm to find out the greatest common divisor of any two numbers. In this lecture we are going to discuss about modular arithmetic. The common properties of modular arithmetics are the modulus and the properties of congruences and other modular arithmetic operations. We will also discuss the implementation of Euclidean algorithm with the modular arithmetic. In the next section we are going to discuss about the prime numbers and Fermat and Euler's theorem. We will discuss how to use the algorithm to test the primality of any number. And we will finish the lecture with the discussion of Chinese Remainder Theorem. At the end of this lecture, we should be able to present an overview of concepts of modular arithmetic and implementation of Euclidean algorithms to find out the greatest common divisor. You should be able to understand the Fermat and the Euler's theorems. And finally, you should be able to explain the Chinese Remainder Theorem for testing of the primality. As I have discussed in the last lecture, the number theory has an exhaustive use in cryptographic algorithm. And this lecture, along with the previous lecture, will provide you sufficient breadth and depth to cover the relevant number theory topics and understand the wide range of their application in cryptography. The last lecture introduced you to the basic concepts of number theory, such as understanding of divisibility and Euclidean algorithm to find out the greatest common divisor. This lecture will introduce you to the arithmetic and other common operators such as primality and testing for primality and Chinese remainder theorem. These concepts are very useful to design asymmetric public key cryptographic algorithms. The concepts and techniques of this number theory are quite abstract, and it is often very difficult to grasp them without proper understanding. Modulus is a common modular arithmetic operator. So we define the modulus of two numbers a and n. So we state that if a is an integer and n is a positive integer, the modulus is, we define it by a mod n to be the remainder when a is divided by n. The integer n is called the modulus. Therefore, for any integer a, we define a is equal to qn, where q was defined as quotient and n is a number that you want to use as a divisor, plus r, which states as the remainder of division. And the property states that the remainder must be greater than equal to 0 and it must be less than n. And quotient is defined as a division of a divided by n and taking the whole number. So a modulus n often also referred as percentage operator. So it is defined as division of a by b and taking the remainder. For example, we take the example here a is equal to 11 and b is equal, n is equal to 7, and we divide both and we get the remainder 4. Similarly, if we divide minus 11 with the 7, we get the modulus 3, remainder 3. So you must be familiar with the division of negative numbers. So if we divide the negative number here, for example, if you want to use the same example as discussed in the slide, you can use 11 and 7. So we divide it using uh, negative quotient, and we get the value minus 14, and then we can find out the remainder. So in this case you get the remainder or modulus 3. Two integers a and b are said to be congruent modulo n if you satisfy this property. That means if a modulus n is equal to b modulo n. This can also be written as a is equal to b modulo n square. So if you have two numbers a and b and you divide with the common number n, and if the remainder or modulo is same for both numbers, we say that the both numbers are modulo congruent of each other. So if we take the example here 73 and 4, and we use the modulus and 23, we say a is equal to 73, b is equal to 4, and we divide the both numbers by 23, we get the remainder 4. So 73 and 4 are modular congruent of each other. Similarly, if we say that a is equal to 0 modulus n, that means b is equal to 0, so we can say n divides a and there is no remainder, that means remainder is equal to 0. So we can take any example. For example, if we have a is equal to 10 and b is equal to 0, and we can take n is equal to 10, so that it can fully divide the a, or you can take the n is equal to 5. So if you divide b by 5, we get the modulo 0, and if we divide a by n, we get the modulo 0. Similarly, if you use the negative division here, you can see that you hold this congruent property on both the numbers described as a is equal to 21 and b is equal to 9. So if you uh, perform the modulus operation, it is very simple. For 21, if you divide it by 10, you get the remainder 1. Similarly, if you use the negative number 9 and divide it by 10, you can use the negative division and you get the same modulus n. So 21 and minus 9 are modulus congruent of each other. So congruence have following properties. For number one property states that if A is modulus congruent of B mod n, if and only if n can divide A minus B. Slide contains a little mistake here. So n divides a minus b, then the a and b will be modulus congruent of each other. You can take any example here. For example, as discussed in the slide, you can use the 23 and 8. If you set a is equal to 23 and b is equal to 8, and you set n is equal to 5, you get the value. These are modularly congruent of each other because they have the same remainder as 3, and they are also hold the first. They also hold the first property. A is modularly congruent of b, and if a n divides a minus b. So if you minus A from B, you get the value 23 minus 8 is equal to 15. So which is a multiple of n 5 plus 3. So n will be able to divide A minus B. The second property states that A is modulus congruent of B. It also implies that B is the modulus congruent of A. So if minus 11 and 5 are taken as values, and you can use the value of n is equal to 8, and you can see they both are modulus congruent. If you divide the value 5 by 8, you get the remainder 5, and similarly if you divide the value 11 minus 11 by 8, you get the modulus a 5 again. And if you use this property in the reverse direction, say 5 is modulus congruent of minus 11 to 8, so this property will also hold. So the property also holds in the transitive domain. So if A is modulus congruent of P mod n and B is modulus congruent of C mod n, it implies that A will hold for your C mod n. So you can verify this property on your own using any values of A, B and C. So modular arithmetic exhibits the following properties for summation, subtraction and deletion. It means if you divide the two separate numbers and take the modulus of them, you can also take the sum or you can also subtract them or multiply them, and you can divide with the same number modulus, and you hold the property for separate division and the combined division. So for example, if you take the first example, A mod n is defined by a remainder, you can say remainder of A, and B mod n is divided is represented as a or of B. It means remainder of B when we divide it by n. So you can write that A is equal to remainder of A and plus j multiplied by n. So j is any integer and n is the divisor. Similarly, for B you can write it B is the number and R of B is the remainder and K is an integer and n is a divisor. So if you open up these braces A plus B mod n, you can get A is equal to R A plus J n, and B is equal to R B plus K n, and you can take the modulus of the whole, and similarly if you combine these values you get RA plus RB modulus n. However, RA is represented as modulus of A divided by n, as we defined it earlier that RA is the A mod n and RB is considered as B mod n. So if you replace these values here, you get to prove the first property here. Similarly, you can prove the property for subtraction and division. For example, let's take an example for the property number 2. A mod n minus B mod n whole mod n. So you take A is equal to 11, B is equal to 15 and n is equal to 8. So by putting the value here A mod n, you get the value 3, and putting the value here B mod n, you get the value 7, and you divide with the mod 8, that is equal to minus 4 mod 8, which will be equal to 4. So if you take On the composite, you have the value of A 11 and B 15, and you divide with 8, you get the similar result here, so that you can get the final value. You can also use other values to apply the third property that is described for multiplication. So here are some examples. I want you to apply it by yourself. This table presents the value of each number from 0 to 7 with the arithmetic module of 8. You can see that each number has an additive inverse. So you can see a clear pattern in each diagonal when you use two values such as x plus y mod 8. So you can take any two values. For example, you can take a value of x is equal to 3, and you can take a value of y is equal to 5. So if you add these two values and take the modulus, you can get the value 0. So you can identify it here. Or you can use any other value. For example, 6 plus 4, you can get the value 10, and you can take the modulus by 8, and you will get the remainder 2. So for any number, there is a clear pattern in the diagonal for additive modular arithmetic described. Similarly, the entries in the multiplication tables are also straightforward. In modular arithmetic mod 8, the multiplicator inverse of x is the integer y, such that x cross y mod 8 is equal to 0. Sorry, in the multiplication case it will be is equal to 1. In additive case it is equal to 0. Now you can find out the multiplicative inverse of an integer from multiplication table. Scan across the matrix in the row for the integer and find out the value 1. The integer at the top of the column is the multiplicative inverse. Thus 3 cross 3 mod 8 is equal to 1. Similarly, you can see 5 cross 5 mod 8 is equal to 1, and 3 cross 3 mod 8 is equal to 1, and 1 cross 1 mod 8 is equal to 1. From here you can observe the pattern between the two tables. In the additive inverse, the table showed additive inverse of each of the number. However, in the multiplicative modulus 8, not all integers of mod 8 have multiplicative inverse. So this table shows a comparison of previous two tables such as additive inverse of modulus 8 and multiplicative inverse of modulus 8. So the property says that for any number there should be an additive inverse such that modulus of that number should exist. So if you take any two numbers, for example, this modulus should be equal to 0 for the additive inverse to exist. So if you take any two numbers, for example 3 plus 5 modulus 8, you can get the 0. You can try with any other two numbers. In the other case, as we discussed in the previous slide, that there exists a multiplicative inverse for only sum of the numbers. For example, if you take 5 cross 5 mod 8, you can get additive inverse that is equal to 1 in this case. So if you take any another case, for example this, you can get 6 plus 6 is equal to 36 divided by 8, and you get the value 4, which is not equal to 1. So you have no additive inverse, sorry, multiplicative inverse of the number 6. This table also presents the properties of modular arithmetic for any integer in the domain. So the property exists for the commutative loss. So if you have two numbers w and x and you take the modulus with n, you can take it in the commutative property for addition and multiplication. That means w plus x mod n is equal to x plus w mod n. It also holds for the associative law, such as this: w plus x plus y is also equal to w plus x plus y, and it holds for the multiplication, and it also holds for the distributive law, such as w plus xy is equal to w plus multiplied by x and w multiplied by y. And there is an identity for each number in modulus, such as you add 0 in the number, there should be no change in the modulus, and if you multiply by number with the 1, there should be no change in the modulus. And there exists an additive inverse for each number in in the domain, and there exists a z such that w plus z is equal to 0 mod n. So this table presents an extended example of Euclidean algorithm. So before looking into it, let's recall what the Euclidean algorithm was. The Euclidean algorithm can be based on the following theorem: for any integers a and b with a is greater than b, which is greater than 0. So first condition we set in the Euclidean algorithm, that if a is greater than 0, then we divide a by b. If a is not greater than 0, we replace the values of a and b. This algorithm states that GCD of any two numbers a and b can be described as GCD of b and a mod b, which is similar to the replacement of a is equal to b and b is equal to a in the other cases. So if we want to find out the greatest common divisor of any two numbers, such as GCD of 55 or 22, we can use the previous form that said GCD can be equal to, for second number b, and modulus of first number with b. So if we divide this 55 with the 22, we get the modulus 11. So GCD of 22 comma 11 will be 11. So 11 will be the greatest common divisor of 11 and 22. So you can verify that this algorithm holds for the initial value we set. 11 is the greatest common divisor for the 22 and 55. We now proceed to look at the extension of Euclidean algorithm. So it will be an extended version of Euclidean algorithm that will be important for later computation in the area of finite fields and in the encryption algorithm, different encryption algorithm. For given integers a and b, the extended Euclidean algorithm not only calculates the greatest common divisor but also two additional integers x and y that satisfy this. The equation is very much similar, so we find the greatest common divisor by GCD Euclidean algorithm of A and B. So it states that it will be a number A multiplied by some integer x and B multiplied by some integer y. So it should be clear that x and y will have the opposite sign to decrease the value to the greatest common divisor. If they have the same sign, the value will be a greater value than the greatest common divisor. So before examining the algorithm, let's look at the sum of the values of x and y when a is equal to given some number and b is equal to given another number. Note that the GCD of these two numbers, this will be a greatest common divisor. Here is a common example. So GCD of 42 and 30 is described as 6. So 6 is a number that divides both of the numbers a and b. So this can also be written in the previous form of application, ax plus by. So a is 42, b is 30. So we can use any of the x and y values to find out the greatest common divisor here. So if you take the values of x from -3 to 3 and values of y also from -3 to 3, you can see that any of the product and summed up number will be divided by the number 6. You will observe that all the values will be divisible by 6, and this is not surprising. Why this is not surprising? Because 42 and 30 are divisible by 6. Therefore if you multiply by any of the value with any of the number in this range or any other range, they will be the product of a number that is divisible by 6, and that number will also be divisible by 6. So if you draw the table in this form, for example, taking the values of -3, -2, -1, so on to 3. Similarly, -3, -2, -1, so on to 3. And you draw a table like this, and you have to find out the minimum value to uh, find out the greatest common divisor. For example, in this case, the greatest common divisor value will be 6. The extended Euclidean algorithm also works on the same principle, and we go through the sequence of divisions indicated by the equation presented here, and we assume that at each step we can find out the integer x and y that satisfy the equation presented as ax plus by, and that will be equal to a value that is actually divisible by the greatest common divisor. So extended Euclidean algorithm uses the same equation as ax plus b, and the equation for remainder that is equal to qn plus r. So this table also presents an example of extended Euclidean algorithm. In each row we calculate a new remainder r of I based on the remainders of previous two rows, named as r of I minus 1 and r of I minus 2. To start the algorithm, we need to find the values of r0. So this column actually represents time. So time step. For calculating the remainder of each row, we find out we calculate the remainders from the previous two rows. So to start the algorithm, we need to find out the values of r minus 1 and r minus 2. So at first step, we set the remainder r is equal to, or minus 1 is equal to a. In our case, a is equal to 1750 9. To satisfy this, we have our equation ax plus by. So if we set the value of a is equal to 1759 and a value of x should be equal to 1, that will be equal to 1759, plus we need a term 0, so we can set the value of y is equal to 0 and b can be any value, so the total sum will be equal to 1759. So in the next step, we set the value of r0 is equal to b. So in this case, our value of b is equal to 550. So the value of can be also uh, formulated by using the same equation ax plus by. So we have the value of b is equal to 550. So we need the value of y that was in the previous section we set in the equation and the value of x set in the previous section. But to calculate the value for this equation, we use the current step as x is equal to 0 and y is equal to 1. So if we put the values of a that was 1759 and x is equal to 0, we get the first term ax is equal to 0 and we put the value of b 550 and value of y is equal to 1, we get the value 550. So that starts our algorithm. So now we use two equations. R stands for remainder, that will be b mod, sorry, a mod. So remainder can be calculated using the equation r is equal to a mod b, and the value of x can be calculated using the previous value of x and subtracting it from the actual quotient that we obtained in the previous step. Similarly, value of y can be used calculated using the previous value of y subtracted by the value of the quotient. So performing these steps at each iteration, we get the value of r, it's 109, and we divide it with using the quotient. This, and we get the values of x and y using the equation. And then we use again the values of previous x and y and the values of r. So r is equal to a, and in this case r is equal to b. So to observe the overall algorithm, we find out the minimum value of the remainder, that will be the greatest common divisor of both the values. So in this case, we get uh, to the step number 4, and we can find out the greatest common divisor, that is equal to 1, and the value of x for that point is equal to 111, and the value of y is equal to 355. Prime numbers only have the divisor of 1 in itself. They cannot be written as a product of any other number. The prime numbers are central to the number theory, and any integer, say p, that should be greater than 1 is a prime number if and only if its divisors are 1 in positive or 1 in negative. So any integer a can be, which is a positive number and greater than 1, can be factored into a unique way, such as a is composed of any uh, sequence of numbers. For example, if we take the number 6, that can be composed of 1 cross 2 cross 3, uh, where p1 is less than p2 and which is less than p3, which is the similar case over here. This is known as the fundamental theorem of arithmetic. This table represents the prime numbers under 2000, and you can see all the prime numbers. And you are very much familiar with the properties of prime numbers, that they are only divisible by itself and the number 1. The two theorems that play important roles in the public key cryptography are Fermat's theorem and Euler's theorem. Fermat's theorem states that if P is a prime and A is a positive integer not divisible by P, then A raised to power P minus 1 is equal to 1 mod P. So if you consider a set of positive integers that are less than our prime number P and multiply each element with any positive number A and take the modulus with P, and to get the set of these values you will have a set. None of the elements of this set is equal to 0, because if you divide any number with the modulus P, that is a prime number, you will not get the remainder 0. So we will conclude that the set will consist of all positive integer numbers with no two elements are equal, and it will start from 1 to the actually the range of P. For example, if we have P is equal to 7, we will have 1 2 3 6, and all these number will not be able to divided by P. For example, we take the example of a prime number 19, and we take any positive number A such as 7, and we multiply with any other positive number that is less than equal to 19. For example, if we multiply 7 by 4 or 2, we get if we multiply by 7, we get the 49, and if 49 is also uh, modulus is not equal to modulus of P19, because it does not divide 7 or 49. The alternate form of the Fermat's theorem is represented as if P is prime again and A is a positive integer, then A raised to power P will be equal to A mod P. In the similar case, you can take the P 17 and you can take the power of any positive number in the domain from 1 to 19, and you will have the same property. This theorem is very useful to find out the primality of two numbers, such as in this case we find out that any number in which is a prime number P can have a set of numbers which are less than this number and are a positive number can also have the must be primal to each other. This table presents some of the values from Euler Totient function. The function is written as phi of n, and it is defined as the number of positive integers less than n and relatively prime to n. That means that any number have your totient function phi of n, and the number will be less than n and will be relatively prime to n. By convention, phi of n is equal to 1. So if a number is prime, all the positive integers from 1 through that number are relatively prime to that number. Therefore, if we take any example of prime number here, for example, if we take the 7, all the numbers from 1 to 7 will be a relative prime of each this number 7. So if we determine the totient function of any number that is not prime, we list all the positive integers less than that number that are relatively prime to it. The case of 9 here, and we list the numbers that are relatively prime to it. So number will be 1, 2, 4, 5, 7, 8. So these numbers are relatively prime to it. So there are total 6 numbers for this number 9. So you can verify any of the other number presented in the table using the same formula. So this leads us to the Euler's theorem that states that every number a and number n that are relatively prime to each other have the property equal to this. So we take the power of Gaussian function with over any positive number that is less than the prime number, and it holds the property of mod n. That means the both number will be prime to each other. The alternate form can also be expressed as a raised to power n plus 1, and that will be a mod n. This represents the same case that any number that are prime to each other. For example, in the last example we see 6 and 7 are prime to each other, and they will hold the property that they will be divisible by one common divisor that will be equal to 1. Or any alternate form can be written. We have the uh, positive number a that can be represented in a prime number p, for example 7 again, and we have the numbers 5 and 7. This can all be divided by their respective numbers such as 5 or 7. Because a is relatively prime to n, and any number x relatively prime to n is multiplied by that positive number a must also be relatively prime to n. Thus, all the numbers are generated in the set are less than the number n, and that are relatively prime to n. So let's put the values. For example, if we take the value of a is equal to 3, and let's say n is equal to 10, and we find out the quotient function for the n, and that will be equal to, let's say in the 10 we have the relative primes of 1, 3, 7 and 9. So there will be 4 quotients of number 10. So apply this formula, a raised to power 5, and that will be equal to 3 raised to power 4, and we will get the value 81. So take the right side of the equation, 1 mod n. So 1 mod 10 is equal to 1 again. So you can verify this function using this example. So if you divide 81 by 10, you get the remainder 1, and if you divide 1 by 10, you get the remainder 1. So these two numbers will be modulus congruent of each other. Similarly, consider the next example. We have the same values. For example, a is equal to 3, n is equal to 10, and we find out the quotient of n is that was equal to 4. So putting the values in the equation, we get a raised to power n plus 1, that will be equal to 3 raised to power 4 plus 1, that will be 5. So we get the value 243. uh, I think it is like 81 multiplied by 3 will be 243, and we divide with the modulus 10, and we get the remainder 3. So if we put on the value in the right side of the equation, 3 mod 10, we get the value 3. So again, this can be verified here. So for many cryptographic algorithms, it is very necessary to select one or more very large prime numbers at random. However, finding out such large prime numbers is quite a difficult task. There is no simple solution exists to accomplish this task. However, certain approaches have been presented to solve out the problem. One attractive and popular algorithm is represented as Miller-Robin algorithm. You can be very surprised to learn that this algorithm yields a number that is not necessarily a prime number. However, the algorithm can yield a number that is almost certainly a prime. We can make reference to the deterministic algorithm to find out the finding the prime numbers. So this algorithm is typically used to test a large number to check whether it is a prime number or not. This algorithm leads to the conclusion that if n is prime, then either the first element in the list of residues automators modulo n is equal to 1 or some element in the list equals to n minus 1. Otherwise, for example, this can be the first condition and this can be second condition. Otherwise, otherwise the number will be composite. That means it will not be a prime number. So algorithm starts by finding an integer k, a q quotient with k must be greater than 0, that must be positive, and q must be an odd number, so that property holds n minus 1 is equal to 2 raised to power k q. Then in the next step you select a random integer a, that a is in the range from 1 to a minus n minus 1. So in the next step you take the mod of a raised to power quotient q with the n, and if that mod is equal to 1 you return that this is inconclusive and the number is maybe a prime number. If that is not the case, you run a loop from 1 to that 0 to that positive number, and you take the power of your number, multiply by some another integer j, and with the quotient q, and take a mod, and if that number is equal to n minus 1 you can return the number can be inconclusive. So if these two conditions are not met, there is a certain chance that the number will be a composite number. So let's apply this algorithm to an example. So we take a prime number that we know, but we want to verify the algorithm. So take the number n is equal to 29. We can find out the n minus 1, that will be equal to 28, and we can verify this equation, that is will be equal to 2 raised to power k q. So we take the value of 2 raised to power 2, and q must be odd, that will be equal to 7. So we have the value 28. So let's try a random integer from a from 1 to n minus 1, that is equal to 28. So we set the value of a is equal to a random number, say 10. So in the third step we compute a raised to power q. We have a is equal to 10 and q is equal to 7, and we take the mod with the number n, that was equal to mod 29. So after calculation we found out that the number is 17. So we check the condition, that is whether is it 1 or not. So it is not 1. So we continue the test and we reach to the loop, and we apply the second step, that states that take the power of the number. So we had 10 raised to power 7 power 2, and we take the mod with 29. So in this case we get the result 28, which is equal to n minus 1. So we return that the number is the result is inconclusive. So we can say that the number 29 is a prime number. Similarly, you can apply this algorithm to check out the primality of a composite number. For example, we want to apply the primality of a number 221. So n minus 1 will be 220, and we put the values in this equation. So we get 2 raised to power 2, and we get the odd number of q, that is equal to 55. So we take another random values from 1 to 220. Let's say we take a is equal to 5. So we take the power of 5 with the q, that was 55, and we take the mod with the 221. So in this case of calculations, we get a value of 112, so which is not equal to 1. So we proceed into the loop and we apply the second step. So we have the value 5 raised to power 2 raised to power 55 mod n is equal to 221, and we get the value after calculation, that is 168. So this condition also does not passes, so we return that number is a composite number. This algorithm is not error free, and it can also tell that a prime number is not a prime number and do in the reverse order. For example, it can tell a composite number that it is a prime number. So we can use this algorithm to predict with some confidence that whether or not an integer is prime. To improve the performance of this algorithm, we must only run the algorithm once if it returns a composite return in return. However, we should return the algorithm multiple times if it is returning inconclusive to confirm with a high degree of confidence that the number is a prime number. Another important algorithm or theorem in the cryptographic algorithm is Chinese Remainder Theorem. It is believed to be have discovered by the Chinese mathematician Sun Tzu in around 100 AD. One of the most useful results of the number theory are presented using Chinese Remainder Theorem. It says that it is possible to reconstruct integers in a certain range from their residues modulo or set of pairwise relatively prime moduli, and it can be stated in several ways. On the overall, Chinese remainder theorem provides a way to manipulate the potentially very large numbers mod m in terms of tuples in a smaller number. This algorithm is very useful when your m number is 150 digits or more. However, it is necessary to know beforehand the factorization of m. This slide shows a table of Chinese remainder theorem applied to a number modulo 19, a prime number for all the positive numbers a less than 19. The length of sequence of each base value is indicated by a shading. All the sequences end in 1. This is consistent with the reasoning that uh, that this is consistent with the reasoning of the preceding few examples. For example, you can see that each of the shading area ends in 1. In other words, you end the Chinese remainder theorem when you reach the value 1. Another important point is the length of sequence divides tangent of 19 is equal to 18. That means you will have 18 values for the remainder, prime remainder 19. That is an integral part or integral number of sequences occur in each row of the table. Some of the sequences are of length 18. For example, you can see the number 2, 3, 13, 14 and 15 have the length 18. In this case, it is said the base of integer a generates the set of non-zero integers modulo 19. Each such integer is called a primitive root of modulo 19. More generally, you can say that the highest possible exponent to which a number can belong, mod n, is totient function of n. If the number in this order is referred as primitive root of n, the importance of the notation a is primitive root of n. So you take the power of each number. For example, if you want to know the Chinese remainder for the number 1, you take the value 1, and there is no number that can exceed the 1 by taking the value of a is equal to 1 and taking the powers up to uh, n minus 1, that is equal to 18. So you will only get one Chinese remainder theorem for each of the power. That means 1 divided by 19, and you will get the remainder 1. In the similar case for 2, you can experience that a is equal to 2, and if you square it 4, you get the remainder 4. If you cube it, you get the remainder 8, and with the power 4 you get the remainder 16. With the power 5 you get 13, so that is equal to 32 modulus 19, you get the remainder 13. Similarly, for 64 you will get the remainder 7, because 19 cross 3 is 57, and so on. And at the power 18 you will get to able to get your remainder to 1. Same is the case for 3 and up to so on. So in the final case, if you take the values of 18 and you get the remainder, when you take the square with this value and you get the remainder 1, and you stop it here. So that concludes today's lecture, and it provided you a summary of modular arithmetic. We started with the modulus, and we learned some property of congruences. Modular arithmetic operation and properties have been seen, and we applied the Euclidean and extended Euclidean algorithm to find the greatest common divisors. Then we studied a few concepts about the prime numbers, and we discussed some algorithms to check the primality of the algorithms. The most important algorithms were Fermat's theorem, Euler totient function, and the Eulers theorem. And we also tried on an algorithm for testing primality. It's called Miller-Rabin theorem. And we concluded the lecture with some description of Chinese Remainder Theorem. So if you want to study more, you can read the chapter 2 of the recommended questions you can ask in the question and answer session.